Here we have a picture of a tall light post in Kansas. And from The Wizard of Oz, we know that Kansas is a windy place, right? And so the DOT in Kansas, and I don't pretend to be an expert on this, but has an issue with fatigue cracks growing around the edges of these inspection ports because they're very windy, right? And so it's exciting the light pole on the interstate. And so they were interested in monitoring the vibration. So a colleague of mine actually put some sensors on this and monitored it, right? And so this is what the time series signal looks like. This is what the vibrations look like through time. And then this is what they were able to extract in the frequency space. And so you have kind of first mode, second mode, third mode, right? Maybe this is like a fourth mode. That depends a little bit on how you do your modeling and how the sensors are set up. But this is an external simulation, right? And so you have wind that's coming in kind of all along the pole, but maybe at different profiles and maybe at different frequencies. Also, you're going to have eddies, right? So you're going to have things that currents that clip around the pole, but your pole has a different diameter all the way up, right? So a certain frequency of component that's in the wind at a lower frequency won't be in the same component at the higher frequency, right? Because a different diameter will react differently to the wind. One of the reasons you make poles tapered is you want it to be excited at different frequencies, right? We haven't talked too much about resonance yet, but if all of your pole is one diameter and it all gets excited at one frequency, right, then it has a potential to go into resonance at that frequency. And so if you have a varying diameter, then what you can get is you can distribute the energy to different frequency components and try to keep your system out of resonance, or at least further away from resonance.